you've got this 1 by 1 square. And the density of the square at the point x comma y is given by the function e to the maximum of x comma y squared, I believe. Double check. Yeah. And we want to find the mass of this thing. So we know how to find mass. Mass in general is the integral of density. Now there's a little bit more to it than that, right? Like there's a dx or a dy here, d something. Let's say dx. The problem is, well, there's a couple problems. Basically, you have to have like your shape as well. You have to have the density times essentially the area. So I should back it up a little bit. I should say, so what if we had like a vertical strip? Well, then the mass of that strip would be the area of the strip, which is the height, 1 times the thickness, dx times the density. And then the total mass normally would be the integral of that from 0 to 1. The problem is the density doesn't always depend on x, it depends on x and y. So kind of the key observation you have to make here before you can do this is you have to break this up into sections where the mass is one thing versus the other thing. So let me show you how I can break this up. I'm going to look at the line y equals x. So let me ask you guys, if I pick a point, say up here, above the line y equals x, what's true at that point? Is it true that x is bigger than y, or is it true that y is bigger than x? Which one of those is true if I'm above the line y equals x? One of them is true. One. Right. Y is definitely bigger than x here. You can even be more, you can try to make your life easier and say pick this point here, which is the point 0, 1, and then it's very obvious that y is bigger than x. So up here, y is bigger than x. And over here, x is bigger than y. We're working on this problem where we're asked to find the mass of this 1 by 1 square whose density is given by the function e to the maximum of x comma y squared. I believe this is from a worksheet, I'm guessing from Morris's class, but I don't actually know. I've seen this problem before though, in various classes. So in this orange region up here, y is bigger than x. So in this orange region up here, the maximum of x and y is y. Totally true. If y is bigger than x, the maximum of x and y is y. So for this orange region up here, the mass of, say, the orange region, well, we're going to have to do in terms of y, because our density is in terms of y, which means we're going to need a horizontal strip. All right, so the area of that strip is the length of it, so it's the right minus the left, so that's going to be x equal to y minus x equal to 0. That's your length, y minus 0. There's your thickness, or your width, dy, and your density is just e to the y squared. So that's the mass of that rectangle. And if you want to find the entire mass of this upper part, it's going to be the integral from as low as 0 to as high as 1 of e to the y squared times y. And I think that's something everyone is capable of integrating with a U-substitution. On the other hand, if we're down here in this red region, where x is bigger than y, then we're going to have to do things in terms of x. So we're going to use a vertical rectangle, and the mass of that vertical rectangle in red is going to be, well, the height, which is going to be x minus 0, y equals x minus y equals 0. The density, which is, well, since x is bigger than y, the density now is going to be e to the x squared times the width, which is dx. And then the total mass is going to be the integral of that from as far left as 0 to as far left as far right as 1. Notably, these integrals are the same. They just have different variables. So once you've calculated this one, you can just double it to get your answer. So that's how you would do this problem where your density is the e to the maximum of xy quantity squared. It's a little bit tricky, but that's how you do it. I'm going to leave it so you guys can definitely integrate that yourselves. I'm going to not finish that part. Okay. Let's look at some differential equations questions that people have asked. At least one. I'm going to change this one up just a little bit. Yeah, so here's a variation on a question I was given. Water leaks out of a tank at a rate proportional to the cube of the remaining volume of water. Okay. Write down a differential equation that models the situation. Be sure to say exactly what each variable represents. Okay. So let's see. So let's say that W is, or let's actually say W of T is the amount of water, remaining in the tank at time t, where T is measured in, I don't know. We're not given, yeah. Well, they're using time and days. Okay, well, we'll figure that out in a minute. So if water leaks out of the tank proportional to the amount of, proportional to the cube of the remaining volume, then we know that dW dt, the rate of change of water, or how fast the water is leaking out, is going to be a multiple, a constant multiple of the amount of water in the tank. So the rate of change of the water in the tank is proportional to the cube of the amount of water in the tank. Okay, we can definitely solve this. So I'm going to separate my variables. So I'm going to say 1 over W cubed dW equals K dt, because we are asked to solve this. So here's my differential equation. Here's me solving it. So then let's see, I'm going to integrate both sides. Integral of W to the minus third is W to the minus second divided by -2. Integral of K is KT plus a constant. And now here's where we're going to, let's do a little bit of manipulating here. So I'm going to rewrite this as -1 over 2W squared equals KT plus C. Yeah, thinking it a little bit gnarly here. Let's multiply both sides by -2. So 1 over W squared equals negative 2 KT minus 2C. And here's where you might just say that's a new constant. That's a new constant. That would probably be fine. Yeah. This is where things always get like a little bit dicey. Is the second, I suppose I should give you an initial condition. So let's say that we know that after, so here's the problem, is time measure, what's time measurement? They give an initial condition like after 1 day. So yeah. So initially, well, that's easy enough. Sorry. So initially, there are, let's say, 300 liters, and 1 day later, 60 liters have leaked out. Sure. So when time equals 0, that's initially, we have 300 liters. Okay. So we know that 1 over 300 squared equals negative 2C. So this constant here is 1 over 300 squared. So I don't actually need to solve for C. I can just be like, okay, boom, negative 2C is 1 over 300 squared. So I'm going to rewrite this equation as 1 over W squared equals negative 2 KT plus 1 over 300 squared. Okay. And then I know that 1 day later, 60 liters have leaked out. So when time is, I guess we'll measure time in days. So when T is 1, T is 1. Well, it's not that W is equal to 60, it's that we've lost 60. So we're actually going to have 240 liters left. And W, which I erased, is the amount of volume we still have remaining. So when time equals 1, you have 1 over 240 squared equal to negative 2K plus 1 over 300 squared. These numbers are not nice, mostly because I just made it up. We're solving for this, right? We're going to get negative 2K equal to 1 over 240 squared minus 1 over 300 squared. Again, not very nice. That's fine. So here's what my equation looks like before solving for W. 1 over W squared equals negative 2K, which is this gross number here. 1 over 240 squared minus 1 over 300 squared times T plus 1 over 300 squared. And then you would solve for W, you would take the reciprocal of both sides, which is going to be gross. So you have W squared equal to the reciprocal of all that, which is not just, you don't get to flip each fraction. The reciprocal of all that is literally, I'm just going to write it all to the negative first power. 1 over 240 squared minus 1 over 300 squared times T and minus 1 over 300 squared, all to the negative 1. And then to solve for W, we take the square root of that. So that's how you would do a problem kind of like that. Yeah. That might look kind of hurts. Sorry. It's not good.
James?
Yeah, go ahead.
I have a question. So when we started off the problem, where did the W to the W that was cubed, where did that come from again? Was that from the problem? Or you made it?
The problem said that the rate of change of the problem said that the water was leaking out of the tank. So it's the rate of change of the water at a rate proportional to the cube of the remaining volume of water.
Oh, okay. Thank you, James.
And the actual problem, it's proportional to the square root. So in the actual problem that you guys, that was given in this Morris worksheet, you have something more like dW dt is K times the square root of W. And then you would solve that. It's the same idea. Right. What else do we got here? Let's do some more trig substitution. So I know I erased it, but I'm gonna say it again anyway. That's not what it's right there. And please do, right? If you guys have questions, don't hesitate to ask them. I'm happy to address them. Remind everybody when you're doing a trig sub or when you sorry, and so I think not today, but I think on Thursday we'll finally I think have all the pieces we need to go over kind of the handout where we talk about all the different ways you can think about integrating a thing and kind of what process you go through to say like, do we try this, or this, or this, and then what should we do first? We still need to talk about partial fractions before we can do that. So if you're thinking of problems in trig sub, there are 3 different possibilities you're looking for. You're looking to have something like 1 minus something squared, because 1 minus sine squared theta equals cosine squared theta. So if you have 1 minus a variable squared, you're looking to make that variable equal to sine. Or you have 1 plus tangent squared theta equal to secant squared theta. So if you have something, the 1 plus a variable squared, you want to make that variable tangent. And finally, if you have your variable squared minus 1, which is secant squared theta minus 1 equals tangent squared theta, you're looking to make your variable secant so you can have that trigonometry show up. So let's look at some examples. There's some pretty, I will say, your homework definitely has some fairly gnarly looking examples. I'm not gonna lie, there are some funky questions for sure. Yeah, real funky. So let's look at something like, I don't know. And so the problem is, right? That's not the problem. It's just the problem is me. I know. So let me grab the good old textbook. Maybe there's an extra problem. One moment. We've got lots of problems here, but I feel like if we grab another one, so yeah. Let's see what kind of gnarliness we have in the textbook here. Sure, that looks great. Let's try this one. Let's try the integral of 1 minus x squared to the 3/2 power over x to the 6th. Okay, so I see a 1 minus my variable squared. I want to get 1 minus sine squared. That is the one I'm looking for. To turn this into that, I'm going to let x equal sine of theta. So we're going to make the trig substitution, x equals to sine of theta. And then immediately, the next thing we always want to write down is that dx, the derivative of sine of theta, is cosine of theta. And then we start replacing things. So I'm going to get 1 minus. So the nice thing about this, you don't have to worry about like making the U-Substitution kind of work out, right? It's just all, you just throw it all in. And all my x's become sines. So you get 1 minus sine squared theta to the 3/2. I get sine to the 6th theta in the bottom. And dx is cosine theta d theta. Okay. Now it's vital that we simplify things. The whole reason we picked x equal to sine theta was because 1 minus sine squared theta is a trig identity and it's equal to cosine squared theta. So this is going to equal the integral of cosine squared theta to the 3/2 power times another cosine theta, d theta, all over sine to the 6th. Okay, cosine squared to the 3/2 is cosine to the 3rd times another cosine is cosine to the 4th. This is going to be cosine to the 4th theta over sine to the 6th theta, which then looks a little dicey. Like I was doing a problem similar to someone else earlier, and I really didn't know what to do next. So here's what we figured out though. We can write this as cotangent and cosecant. So I know we talked about powers of trig integrals like tangent, secant, or sine and cosine. Well, we should have apparently also talked about cotangent and cosecant. I'm just going to remind you that the rules are the same, meaning when you have powers of sine and cosine or secant and tangent, or cosecant and cotangent, you're looking to make a U-substitution so that your non-U choice has an even number of leftovers. Let me show you what I mean. So I'm going to write this as, so cosine to the fourth over sine to the fourth. And I'm still left over with the sine squared in the bottom. If cosine over sine is cotangent, so this is the integral of cotangent to the fourth theta, and then 1 over sine is cosecant, so 1 over sine squared is cosecant squared. So now here's the kind of guess. Do we let u equal cosecant? Okay, so let's actually talk it out. If u is cosecant, then our du is cosecant cotangent. So I'll suck up one of those cosecants and one of those cotangents. And since u is cosecant, there'll be an odd number of non-u's left, right? Because I'll use one of those cotangents up. I'll have a cotangent to the third. That's not what I want. I don't want an odd number of non-u's left over. So instead, we should probably pick u equal to cotangent. If u is cotangent of theta, then our du is negative cosecant squared of theta d theta. And negative du is positive cosecant squared theta d theta. And look, once I suck up those two cosecant squareds, how many are left? Well, 0 are left, but 0 is still an even number, so it works. You always want an even number of your non-u thing left over. 0 is the best even number to be left with. They didn't have to deal with it at all. So this is going to become the integral of, let's see, so the cosecant squared theta becomes the minus du. And the cotangent to the fourth is just going to be u to the fourth. Oh, we didn't need quite so much du room there. So we end up with negative u to the fifth over 5. Are we done? Not at all. We still have a bit more to do. So first we have to plug back in what u is equal to. U is cotangent of theta. So let's go ahead and erase this up here since I'm running out of room. So plugging in u equal to cotangent, we have negative cotangent to the fifth theta over 5. Let's see. But the problem is we didn't start with theta as our variable, we started with x as our variable. So we then need to do the triangle thing. So I know that sine of theta equals x over 1. So in my triangle, the opposite should be x, the hypotenuse should be 1, and the third side should be the square root that made you do that in the first place. So it is the square root always of 1 minus x squared for this particular one. You could also use the Pythagorean theorem to figure it out. Cotangent of theta, well, tangent is opposite or adjacent, so cotangent is adjacent or opposite. So I get negative, I'm going to write it as negative 1/5 cotangent, which is the square root of 1 minus x squared over x, all to the 5th power. Let's see. It's kind of gnarly. Yeah, it's a good problem. I like that. Are there questions about what we've done here before we do some more? This next problem I feel like is a lie, but oh yeah. We'll try this one, but I feel like there's something, I feel like in the back of my memory, I'm like, I feel like I know this problem is harder than it actually is. We might start this problem and then have to take a detour. A long detour. Well, let's at least look at it. Okay, so we've got the integral of, yeah, I really feel like this feels like a giant lie, but let's try it. The integral of 8 over 4x squared plus 1 quantity squared. I'll repeat, almost all the time when you're doing trig sub, the thing you're doing in trig sub 4 is inside some sort of root, whether it's a square root, I mean, this one was inside a square root too. It's just a square root. It's cubed. Almost all the time they're in a root, with some exception. The exception usually is when it's something squared plus a number. So here I have a plus, which means I want tangent to be my trig sub, right? And then 1 plus tangent squared theta equals secant squared theta. I always think of plus looks like tangent starts with t. So when I see a plus, I think tangent. So I want to have tangent squared plus 1. So I need 4x squared to equal tangent squared of theta. That's really, I'm always just trying to be like, what do I need? What can I make equal to what so that I get my trig identity happening? So then I can solve for x. X squared is tangent squared over 4. So that x is 1/2 tangent of theta. Now here's the thing. I don't need to be all smart about it and be like, I'm going to plug in x equal to 1/2 tangent of theta. That seems like more work that I need to do. I know that 4x squared is what I chose to equal tangent squared. So when I start writing this out, I'm going to say, well, this is 8 over tangent squared theta plus 1. And dx, well, x is 1/2 tangent theta. So dx is 1/2 secant squared theta d theta. The square here. Maybe this, I guess I'm just imagining. There's something else to imagine where this is. Yeah, there's a different thing. It's anyway. Yeah. I guess I'm thinking of partial fractions and how this can kind of show up, but I'm not going to. So, yeah. Dx is 1/2 secant squared theta. So tangent squared plus 1 is secant squared. So what I have is, let's see, the 8 divided by 2 is going to be 4. And I have a secant squared theta d theta over a secant squared squared, which is secant to the 4th. Cancel 2 of those with 2 of those. So I'm left with 4 times the integral of 1 over secant squared theta. 1 over secant squared is just cosine squared. So this is 4 times the integral of cosine squared theta. Okay. We know how to integrate cosine squared. We have to use the trig identity. Cosine squared theta is 1/2 times 1 plus cosine of 2 theta. 4 times 1/2 is 2. I didn't write the integral. Integral of 1 is theta. Integral of cosine 2 theta is sine of 2 theta divided by 2. So it looks like I got 2 theta plus sine of 2 theta. Now I need to do the triangle thing. And to do the triangle thing, I'm going to recognize that tangent theta, or x equals 1/2 tangent theta. Where can I draw my triangle? I guess I can draw never enough room. Okay, so sorry. I guess I can draw my triangle over here. So I want to solve for tangent. So tangent theta equals 2x. Tangent is opposite of or adjacent. So in my triangle, that's theta. Tangent of theta is 2x divided by 1. Right? If you don't have a fraction, make it a fraction by dividing by 1. So then tangent is opposite over adjacent. And that third side had better be the square root of the thing that made you do the trig sub in the first place. 4x squared plus 4. It does have to be the square root though, right? Because Pythagorean theorem. Okay, so let's see. Actually, I might not even need the triangle. Maybe I should have backed up a minute. I do need the triangle. Theta, we have to use an inverse trig function for. So tangent theta equals 2x. Theta is the inverse tangent of 2x. So it's the inverse tangent of 2x. It's sine of 2 theta. So it might be okay, but it's not okay with me. But it might be okay on web work to say that you get sine of 2 times the inverse tangent of 2x. To me, that just feels lazy. Now, if it works, and sometimes it's fine to be lazy, right? The homework is long. If you don't want to solve for what this is, I totally get that. But what most of the time we usually do here is we use the trig identity for sine of 2 theta. So there's a double angle identity that says sine of 2 theta is 2 times sine of theta times cosine of theta. And then we can say that, oh, we get still the 2, no, that's fine. Right, the 2 times theta, which is 2 times the inverse tangent of 2x, plus sine of 2 theta, which is 2 times sine of theta is 2x over the square root of 4x squared plus 1. Times cosine of theta, which is 1 over the square root of 4x squared plus 1. Plus c. It's kind of gross. Most of these are pretty gross. If you wanted to, you could totally multiply this together. And if you really wanted to, you could write your final answer as 2 times the inverse tangent of 2x plus 2 times 2x is 4x over the square root of 4x squared times the square root of 4x squared plus 1 is 4x squared plus 1. Yeah. I feel like there's a way to do this using partial fractions, but I might just be crazy.
James?
Yeah.
I wanted to quickly ask how you got the 1/2 tan theta. Is that because you just took, when we equaled x, you just took the square root of everything?
Right, exactly. So I started off with, I want 4x squared to be equal to tangent squared. So I divided both sides by 4, and then I took the square root of both sides.
Okay, sounds good. Thank you, James.
Oh, now, other questions?
So James, at the end, you use pretty much trig identities at the end, pretty much.
Yeah.
Okay, so it's pretty much when you see it's convenient, you go ahead and use them.
It's not so much, I wouldn't describe this as being particularly convenient, more as being necessary. So, right, I don't really have any other way to deal with sine of 2 theta other than using the trig identity for it.
Yeah, there's no other thing.
Right. I don't remember who I was helping, I think yesterday, where we ended up getting sine of 4 theta showing up, which was a real pain. But so I don't remember the problem, and I'll just point out, right, like if you ended up getting, so let's say in our answer, instead of this being an answer, let's say our answer was sine of 4 theta, just for fun, If our answer was sine of 4 theta, then we would write that as sine of 2 times 2 theta. Sine of 2 times the thing is 2 times sine of the thing times cosine of the thing, where the thing in this case is 2 theta. And then we'd use the trig identities for each of those as well. So my orange pens seem to be, the orange pens, the problem with the orange pens is they're just never, well, this one's just dead. Maybe that's the problem. Maybe some of these orange pens are just dead. Okay, that one's fine. Then we would say, well, sine of 2 theta is 2 sine theta cosine theta. And cosine of 2 theta, the trig identity for that, or one of the trig identities is cosine squared theta minus sine squared theta. And then you would use this triangle for each of those things. So you get 2 times 2 is 4 times sine of theta is 2x over the square root of 4x squared plus 1. And then cosine theta is 1 over the square root of 4x squared plus 1. And then cosine squared theta is 1 over that squared, so it'd be 1 over 4x squared plus 1. And sine squared theta would be 2x over that squared, so 4x squared over 4x squared plus 1. The point is, right, you have to kind of use these trig identities to help you evaluate these trig substitution problems. There's not really, oftentimes, so especially when you're getting sine of 2 theta or cosine of 2 theta or sine of an even multiple theta, or cosine of an even multiple theta, you can always break it down into just sines and cosines. It just takes a bit of work. Let's look at another one.
James,
Yeah.
before we move on, how did you get 2 theta plus sine 2 theta to equal 2 tan inverse of 2x?
Well, it's not just two inverse tangent, right? That's just what this part is.
Oh,
This
yes.
part is all that down there.
Yeah, yeah. Oh, okay. I forgot. Yeah, we have to, yeah, solve again.
Cool.
Thank you, James.
Of course. Let's see, what other bonkers stuff can we look at here? You all look not super exciting. Sure, let's look at this one. That's that. Let's see, no, sure. Let's say we have the integral of, I want not a sine one, I want a different thing. Let's do something like, yeah, that's good. Sure. Let's do the integral of, where'd you go? X squared over, let's make it more interesting. Let's say x squared minus 9 to the 5 power dx. And we're going to specify that x is larger than 3. Yeah. Yeah. So I know all of you have some, or most of you at least have some sort of problem where it's like this and you have some sort of specification like this. This is actually a clue. If you see this clue, you should automatically think my trig sub is probably a secant. And the reason that's the case is because I don't want to get too into the details because it's not that important. But basically, the inverse secant function has some domain issues. It's actually really because you can define inverse secant in 2 distinct but valid ways. Some people like to define it one way, some people like to define it another way. And depending on how you define it, you get absolute values showing up sometimes. To not have to deal with any of that garbage, we're just going to say that x has to be greater than 3. So that when we take the inverse secant, everything is positive to start with. So if you see a problem like this, 1, don't sweat this. It's just there so that your answer isn't more complicated than it actually needs to be. And 2, if you see something like this, you should probably think it's probably going to be a secant. There might be some other weird ones out there that aren't, but most of the time, if they're giving you a problem that's probably a trig sub and they're specifying a restricted domain for x, it almost always means your trig substitution is secant. So here, I know I want x squared. I want x squared to equal 9 secant squared theta. I really do think it's kind of best to just write down what you want x squared to be, or what you want, whatever is there. So just actually, yeah, let's make it even grosser. I'm going to change it up a little bit. Let's say instead I had a 4x squared here. And then they told me that now the domain is x squared has to be bigger than 3 halves. Instead of trying to be all tricky and figure out what x needs to be, I know that this needs to be 9 secant squared theta. So I'm going to say, okay, 4x squared needs to be 9 secant squared theta. So that when I rewrite this, I get 9 secant squared theta minus 9 to the 5 halves power. Right? That's what I care about happening. Specifically, I'm going to factor out the 9. So I have 9 times secant squared minus 1, all to the 5 halves power. So really, 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 I can't stress enough. If you have something that's looking like a trig sub, just ask yourself, what does the variable part need to be so that you get the trig identity that you want here? And because we know that 9 secant squared minus 9, or 9 times secant squared minus 1, is equal to 9 times tangent squared. That's why we're making that choice. And then the rest of it, then the rest of it we have to kind of work out. So dividing both sides by 4, x squared is 9/4 secant squared theta. Hey, look, there's an x squared right there. Let me go ahead and plug that in right now before I solve for x. In fact, let's do it the smart way. Let's put the 9/4 out in front and the secant squared theta right there. Right, that's totally legit. Now I'm going to solve for x because I still need dx, right? I've seen a lot of people be like, okay, I dealt with that, I dealt with that. That's not, dx is not equal to d theta. Let's figure out what it's equal to. To take the square root of both sides, x is 3/2 secant theta. Dx is 3/2 secant theta, tangent theta, d theta. So I'm going to get a secant theta, tangent theta, d times the 3/2. Questions so far? Do one thing real quick here.
And then just to make sure, does it say 3/2 or 5/2?
That does say 5/2. Sorry,
Oh.
the power or the fraction?
No, the textbook, yeah.
That's a 5/2 power. Yeah, I know. Let me make that a little more explicitly clear. Someday we'll be in person again, and you'll get to see that my writing is equally terrible in person, but slightly easier to read because it's not on a camera.
James, I have a quick question.
Sure.
It's a little bit off topic, but are you doing the co-class for next semester? I mean, quarter?
So next quarter, are you? That's actually a good question. Let me actually. So let me finish this problem, and then we can take a look at that real quick. So I know we have classes set for fall quarter. I just don't remember what we're offering. So let me I'll check on that right after we finish this problem.
Yeah, it's fine. It's fine. Thank you.
Okay. So let's go ahead and see here. So I've got 27/8. And then on top here, I have a secant cube times a tangent. On the bottom here, so 9 to the 5/2 is 3 to the 5th. Let's just put that out in front. So I have an 8 times a 3 to the 5th. I can cancel a bit there, right? 27 is 3 cubed. So I can cancel a 3 cubed there and a 3 cubed there to be left with a 3 squared on the bottom. So the denominator here is 8 times 9, which is 72. Okay. Over here, secant squared minus 1 is tangent squared. Tangent squared to the 5/2 power should be tangent to the 5th. And I will admit, I'm a little worried about where this problem is going, right? Didn't make sure I copied it down from the book correctly. Yeah, I didn't do anything wrong, weird here. So this problem should work out. I just see a question from Ulysses. Yeah, what's up?
Oh yeah, James, I had a quick question. It was like, how come when we set up our 4x squared, how come it wasn't like 3 secant squared theta? Because you know how our formula is if like a squared minus x squared.
Right.
But this time it was just like, I don't know. I'm not sure how to put it in words correctly for it to make sense.
Like what? So are you asking why didn't I pick like x equal to 3?
Yeah. Instead of a 9, why not why wasn't it like a 3?
Well, I did. I just worked my way to there.
Okay.
But the thing is, and this is just a matter of how you like to think of it. I like to think about what trig identity do I need to happen here? I need something minus 9. Oh, I need 9 secant squared minus 9. Right? I know if I have an x squared minus a squared, I need x to equal a secant theta. Right?
Yeah.
Okay. But the problem is, especially here, with that 4 is really jamming me up. I don't want to have to be like, okay, I know that x needs to be a secant theta, but I need to like divide everything. I don't want to factor out a 4. That feels like trash. What I really want to do is just say, I know it's going to be secant because it's variable squared minus a number. And I absolutely know that I need this here to be the same number as that times secant squared. So I'm going to write that down. I'm going to write down that I want 4x squared to equal 9 secant squared of theta.
Yeah. Oh, I guess I see, because you know how you said x equals a secant theta, and we wrote 4x squared equals 9 secant theta.
9 secant squared theta.
Oh yeah, square root of theta. I would have thought, because since for like the variable version we just have a, but not a to the power of 2. That's why it would have only been 3. I don't know if that makes sense.
So typically when they write it, like for example, if someone wrote like the formula for this, they would write it as the integral of, like the square root of a squared minus x squared, and they would say that they would write it as a squared, not a.
Okay.
It's atypical to write this as just a, not a squared.
Okay, that makes sense.
Okay, but really, I would encourage all of you to think about it as just like, what do I need the variable thing to be so that the trig identity works? And that's going to make solving for x I remember doing these problems when I definitely remember doing problems like this many times, and it being very challenging. Like, what does x actually need to be? But divorce yourself from that. You don't actually have to think about what x has to be right away. You can be like, I know I need a trig identity. I know I have 4x squared minus 9. I know I want 9 secant squared theta minus 9. Okay, well, these need to be the same. It works. I feel like it's probably the easiest way to do it. It's the way that's going to be the easiest to then figure out what x actually is. All right. So let's see. So we were here, and I was about to feel like I was going to get stuck. It's all right. Sometimes you get stuck. Let's cancel a tangent. I think it's going to work out. So I said I had 1 over 72 out here because I had 8 times a 3 squared. And I've got the integral of secant cubed theta over tangent to the 4th theta. So it's interesting. In that previous problem we did, we had cosines over sines, and it actually helped us to turn them into cotangents and cosecants, which is not something I've encountered a lot of. Here we have secants over tangents, and it's probably going to help us best to turn them into sines and cosines. So this is going to be 1 over 72 times the integral of secant cubed is going to be 1 over cosine cubed. Tangent to the 4th would be sine to the 4th over cosine to the 4th, but then I have to flip and multiply. So it would be cosine to the 4th over sine to the 4th. Okay, I'm not sure if this is the right way to go. So then that's something that we have to deal with, right? Sometimes you go the wrong way and you have to go back, or at least try to do different. I can cancel 3 of these cosines with 3 of those cosines. So I'm at the point where I have 1 over 72 times the integral of cosine of theta over sine to the 4th of theta d theta. Okay, this is going to feel a little bit bonkers, but I think we have to make it in terms of cotangent and cosecant. So cosine over sine is cotangent, and then 1 over sine cubed is cosecant cubed. That's weird. Like they're definitely kind of tricky problems. So the real kind of, I would say, one of the things you're trying to look for is we really don't want, most of the time we're trying to get our trig functions out of the denominator. So if you have trig functions in the denominator, we often want to rewrite them. Right, so, I mean, and the thing is, you either want sines and cosines, or tangents and secants, or cosecants and cotangents. Like I could have rewritten this as secant cubed times cotangent to the 4th, That wouldn't have helped. I don't want secants and cotangents. So yeah, rewrite this as cosine over sine to the fourth, and then rewrite this as, yeah, cosine over sine. And then we also have a 1 over sine cubed. Okay. Cosine over sine is cotangent. 1 over sine cubed is cosecant cubed theta. And now we have to make a choice. Do we let u equal cosecant or do we let u equal cotangent? Well, if we let u equal cotangent, our derivative is cosecant squared, negative cosecant squared. And after we deal with taking out those two cosecants, we have an odd number of cosecants left over. That's not what we want. We let u equal cosecant of theta. Our du is negative cosecant theta, cotangent theta. So negative du is positive cosecant theta, cotangent theta, d theta. So this is going to become 1 over 72. The cotangent and one of the cosecants become our negative du. That took care of one cotangent and one cosecant. I'm still left with a cosecant squared, which is my u squared. Do I need to say more about that? I'm happy to. Okay. So then we get negative 1 over 72 u cubed over 3 plus c. We get negative, so u was equal to cosecant, so we get negative cosecant cubed theta over 216 plus c. And then finally, we have to figure out what cosecant is. So we draw our triangle. Remembering in our triangle that, well, let's just go back and look instead of trying to remember, that x is equal to 3/2 secant theta. So x equals 3/2 secant theta. Secant is, I would probably rewrite this as x equals 3/2 times 1 over cosine theta, and then multiply by cosine. So cosine theta equals divide by x, 3 over 2x. I would do it like that. So cosine is adjacent over hypotenuse, so I have a 3 here and a 2x here. And then my third side had better be the square root of 4x squared minus 9. It is. This squared is 9, plus this squared is 4x squared minus 9, and 9 plus 4x squared minus 9 is equal to 4x squared, which is the square root of 2x. Or you can just divide that into it. All right, so then cosecant is not opposite of hypotenuse, but hypotenuse over opposite. So this is going to be equal to negative 1 over 216 times cosecant, which is hypotenuse over opposite, to the third power plus c. What a bananas problem.
James, I was wondering if you could explain how you got u squared since du is cosine theta.
Nope, du is not cosine theta.
I mean cosecant theta?
Well, u is cosecant theta.
Yeah, wouldn't that just be the cosecant squared theta? U times du?
Wait, so, well, let's talk about it. So, u squared is cosecant squared. Du is, well, du is negative cosecant theta times cotangent theta. So this u squared is cosecant squared, and this du is negative cosecant theta, cotangent theta, d theta. When I multiply those together, I get cosecant squared times cosecant, which is cosecant cubed, and cotangent.
Oh, I thought it was squared. That's why.
Yeah, I know. I apologize. My writing.
Okay, that makes more sense.
But yeah. another way to see it is we totally could have broken this up as cosecant squared times, then you're left with a cosecant times a cotangent. And then, oh yeah, there's your negative du, and there's your u squared. Yeah. All right, I think we've maybe not said enough about trig substitution, but we certainly said a lot about trig substitution. Let's go ahead and switch gears and start talking about integration by parts, because it's definitely coming at you. We need to talk about it. Let me grab my examples here. So, no, sorry, not integration by parts, partial. Everyone, not just me, everyone always makes that mistake. Integration parts, the word part occurs in both of them. Partial fractions and integration by parts, very different things. Integration by parts is that we use when we have a mixture of things, like the integral of x cubed times sine of x, whereas partial fractions we use when we have a rational function, where the degree on top is less than the degree on the bottom, and bottom factors. Let's look at some examples that actually aren't partial fractions yet. So the idea here is that we can break up a single fraction into the sum of two fractions with denominators that have the original denominator as their common denominator. So for example, I could write 9/14 as, well, 14 factors into 2 and 7. So I can write this as something divided by 2 plus something divided by 7. And I feel like these are actually harder to figure out because you don't have the many tools. Right, if you multiply both sides by 14, you get 9 equal to 7a plus 2b. It looks like both of them can be 1. A equals 1, b equals 1. There might be other options though. In fact, there probably are other options. Not that it really matters, but a could totally be, now I'm like, what kind of crazy things could you do? A could be 3, which could be 21, and then b could be -6. That's interesting. Not really important though. It's not really the point. The point is that you can take a fraction and write it as the sum of fractions that have kind of less complicated denominators. Yeah. So let me give you one more example. We could write 19/20ths as, well, that's 19 divided by 2 times squared times 5. And we could write that as something divided by 2 plus something divided by 2 squared plus something divided by 5. And in this case, again, all of them are 1. Right? You can totally write 19/20ths as 1/2 plus 1/4 plus 1/4. Or you could have said A was 0 and B was 3, because 1/2 plus 1/4 is the same as 3/4. But that's kind of the general gist. If you're trying to take a complicated fraction with a complicated denominator and write it as the sum of fractions that have simpler denominators, that are the factors of the original denominator. So let's look at an example. Now here's the thing. Much like trig substitution, partial fractions is what I often call a method of last resort. Meaning I really want to try just about anything else before I have to use partial fractions. You definitely should always at least look for a U-sub before you start thinking about partial fractions. So let's look at this example. The integral of 2x plus 5 over x squared plus 4x plus 3. Can I do a U-sub? So close, but yet so far. If we let u equal the denominator, our du is 2x plus 4. But we have a 2x plus 5 on top. We're this close to doing a U-sub, but we can't. It doesn't work because the numerator isn't exactly right. 2x plus 5 dx is not the same as 2x plus 4 dx. So we can't multiply it by something so it is the same. So instead, we're going to try partial fractions. Now, the only reason we get to try partial fractions is because our rational function meets the criteria. One, it is, well, three things really. One, it is a rational function, meaning it's a polynomial divided by another polynomial. Two, the degree on top is less than the degree on the bottom, strictly less than. Three, the denominator factors. So we're going to write this as 2x plus 5 divided by x plus 3 times x plus 1 equal to a over x plus 3 plus b over x plus 1. All right. So now the idea is we're going to multiply both sides by the common denominator, which is nice. We're going to multiply everything by x plus 3 times x plus 1. So we multiply this here, the denominators cancel, and you just get 2x plus 5. When you multiply this here, the x plus 3's cancel. So you get a times x plus 1. When you multiply this here, the x plus 1's cancel, and you get b times x plus 3. Now, there are a number of ways of solving for a and b. Here is what I encourage everyone to do. There's really like three things you can do. Two of them are good, one of them is trash. The two that are good, and the one that you should always do first is use convenient values of x, meaning these two things are supposed to be equal to each other no matter what x is equal to. So you could, and it's totally valid, you can let x be whatever number you would like it to be. We're going to pick values of x that make something 0, or what I like to call convenient values of x. And this is 100% the first thing you should always do. In this case, it's all we need to do. So I'm going to let x equal -1. If x is -1, I get 2 times -1 plus 5 equals a times 0 plus b times -1 plus 3. Okay, well, let's see. -2 plus 5 is 3. 0, b times 2. So b is going to be 3/2. Great. Let's now pick the value that makes this part 0. So let's pick x equal to -3. Plugging in x equal to -3, I get -6 plus 5, which is -1. On the right-hand side, I get a times -3 plus 1, so a times -2, plus b times 0. So solving for a, I get a equal to +1/2. There are other methods of doing this as well. You can do, the other method is what's called equating coefficients. And that is a method I like to use if I run out of convenient values of x, which you definitely will sometimes. The equating coefficients method says, well, these are polynomials. These are polynomials that are equal to each other, meaning the amount of each coefficient on each side has to be the same. So on the left, I have 2x plus 5. And on the right, if I multiply this out, I have ax plus a plus bx plus 3b. Grouping the like terms, I have a plus b times x, and I have a plus 3b as my constant term. So then, since this has to equal that, it must be true that 2 equals a plus b, and that 5 equals a plus 3b. And then you can solve this in whatever way you want. I usually like to subtract. If you do this minus this, 2 minus 5 is -3, a minus a is 0a, b minus 3b is -2b. And then divide by -2, you get b equal to 3/2. And then if a plus b equals 2 and b is 3/2, a has to be 1/2. This feels like a little bit more work in this particular situation, but sometimes equating coefficients is super powerful. So definitely my usual process for finding A and B and C and D and whatever is first use every convenient value of X, meaning every value of X that's going to make some factor be 0. If you run out and you still have A, B's, and C's left to find, then we start equating coefficients, meaning say, oh, the amount of X here has to be the amount of X there, the amount of X squared here has to be, right? So anyway, now we can integrate this. This fraction is equal to A over X plus 3 plus B over X plus 1. And we know how to integrate those things. The integral of, so I'm thinking of this as 1/2. And so I don't think you need to write this out. So yeah, so here's where I think you should jump to. You should be able to jump to that this is equal to 1/2 the natural log of the absolute value of X plus 3 plus 3/2 times the natural log of the absolute value of X plus 1. The intermediate step that I'm skipping is factoring out the 1/2 and breaking up the intervals. So breaking them up and factoring out the 1/2 from the first one and the 3/2 from the second one. I don't think you need to show this work at all, but if you want to, you can. So that's the very basic idea, is that we're going to, if we need to use partial fractions, we're going to factor it apart and then try and rewrite that fraction as smaller, simpler fractions. Do another one. Let's say we have the integral of X plus 2 over X squared plus 4X plus 3 again. Could you use partial fractions here? For sure. Do I want to use partial fractions here? Not at all. Because in this case, I can do a U-sum. U is X squared plus 4X plus 3. Du is 2X plus 4 dx. Dividing both sides by 2, 1/2 du is X plus 2 dx. So this becomes the 1/2 the integral of du over u, which is then going to be 1/2 the natural log of the absolute value of u plus c, which is 1/2 the natural log of the absolute value of X squared plus 4X plus 3. You would get the same answer doing partial fractions, but it's a lot more work. Right? Because then you have to be like, all right. So let me just show you. We can do we'll do a partial fractions real quick. So you could do a partial fraction, but again, I want to emphasize here. You don't want to use partial fractions if you can do something else most of the time. But we could totally say this is X plus 2 over X plus 3 times X plus 1. It's equal to A over X plus 3 plus B over X plus 1. Multiply both sides by the common denominator. So on the left, you get X plus 2. On the right, you get A times X plus 1 plus B times X plus 2. Letting X equal -1, you get -1 plus 2 equals A times 0 plus B times 2. Which is going to give me B equal to 1/2. Letting X equal to 3, we're going to get -1 equal to A times -2. So A is also equal to 1/2. So when we integrate this, we can rewrite it as the integral of 1/2 over X plus 3 plus 1/2 over X plus 1. Which is equal to 1/2 natural log of the absolute value of X plus 3 plus 1/2 natural log of the absolute value of X plus 1. Are those the same? They don't look the same. They are the same.
Yeah.
They're the same because we can use the rules of logarithms to put these together. You can factor out a 1/2, and then the natural log of X plus 3 plus the natural log of X plus 1 is the natural log of the absolute value of x plus 3 times x plus 1, which is the same as that. But do it this way if you can. If you can do a U-sub, it's usually the right choice to do a U-sub. You're never going to be sorry you did the U-sub instead of something else. Maybe not never, mostly never. Okay, so the thing about partial fractions is there are not one, not two, not three, but 4 distinct cases of things you might need to do. The first case, the easiest case, is where you have distinct linear factors. So I factor this denominator as x plus 3 to the first times x plus 1 to the first. And they're both linear factors, right? They're x plus or minus a thing. And they're not raised to a higher power, meaning they're distinct. Let's look at a different situation. How much time have we got? Oh yeah, we got enough time. So let me double check this thing here. Cool, yeah. Let's say we have the integral of 3x minus 8 divided by x cubed minus 4x squared. So again, this meets the criteria for partial fractions. I definitely have a rational function whose degree on top is less than the degree on the bottom, and the bottom factors. So I'm going to factor the bottom. It factors as x squared times x minus 4. Now here's the deal. The x minus 4 is fine. Come on. Right, this is a over x minus 4. But this x squared is actually a repeated linear factor, right? This x squared is really x minus 0 squared. And the issue is, I need kind of all the possibilities. Meaning, if I just write that I have b over x squared, I'm going to have problems. Serious problems, like you can't solve this thing kind of problems. Let me show you. If you don't have what the other part you need, this isn't going to work. If you multiply both sides by the common denominator, you get 3x minus 8 on the left. You get a times x squared plus b times x minus 4 on the right. So a has to be 0, right? Because there's no x squared come over here. And b has to be both 3 and negative 2. Sorry, positive 2. B has to be 3 so that we get a 3x. But b has to be 2 so that we get a negative 8. That's not going to work. So we don't have enough pieces to reconstitute our fraction. And the idea here is that we need, when you have a repeated linear factor, meaning a linear factor to a power higher than 1, you need all the lesser powers of it as well. Now this will work. So let's multiply both sides by our common denominator, which is x squared times x minus 4. So multiplying everything by that, we're going to get 3x minus 8 on the left. You're going to get a times x squared. You're going to get b times x minus 4. And you're also going to get a c times x minus 4. And now these examples, where you have a repeated linear factor, are going to require, well, at least in my opinion, the best way to do these is to, one, first use our convenient values of x. That's always the first thing we should do. And then after we've exhausted those, which we will, then use equating coefficients. Someone have a question or a comment?
Yes, James. So my concern was about the x squared term. Wouldn't we want to add a bx since x squared is like not linear?
No. So x squared is linear. It's just tricky.
Oh.
It's really so what you're talking about, which is kind of the next case, which is when you have a factor that's like x squared plus 4. So if you had something like this and some number on top, then for that piece there, that's called an irreducible quadratic factor, meaning it's a factor and you cannot factor it further.
Okay.
But x squared does factor further, right? X squared factor, it's already factored, is the problem. X squared is just x times x.
Oh yeah, that is linear. Okay.
Now, here's the even worse part about this. If you did it the other way, it would technically work out fine here because of how the math works. It doesn't always work, but in this problem, it definitely would. But I want to just, yeah, so when you have an irreducible quadratic, meaning something with an x squared that you cannot factor further, then you have to use the ax plus b or whatever. But when you have something that's just x plus or minus a number, this is x minus 0 to a power, then you have the repeated factor.
Okay, yeah, that makes sense, James. Thank you.
Yeah. So now we're going to use our convenient values. I'm going to use x equal to 0. I'm going to get -8 on the left. I'm going to get 0 plus b times -4 plus 0. So I'm going to get b equal to 2. Then I'm going to use x equal to 4. 3 times 4 is 12. 12 minus 8 is 4. A times 4 squared is a times 16. And b times 0 plus c times 0. So when you use convenient values, everything but one thing should cancel out. So you're going to get a equals 4/16, which is 1/4. And now I've run out of convenient values. So here's what some people will do, which is not my favorite. If you only have one thing left to find, which we do, right? We found A, we found B, we only have C to find. Technically, it totally works to pick any other number for x. I would probably pick x equal to 1, and then plug in. Actually, I might pick x equal to 2. So here's one way you can do it. You can pick x equal to 2, and say, okay, 3 times 2 is 6 minus 8 is -2. A is 1/4 times 2 squared plus b is 2 times 2 minus 4 plus c times 2 times 2 minus 4. And then I can solve for c. I don't want to do that. Not because I can't, but because there's an easier way. So the easier way, once you have used up all of your easy values of x, then I like to shift gears to what I call equating coefficients. So these are polynomials. They're equal to each other, which means the amount of each power of x on one side has to be the same as the amount of power of x on the other side. So I always look for the highest power because there's usually the least amount of terms with it. How much x, so what's the highest power of x? X squared. How much x squared do I have on the left?
None.
None, right? So I have 0x squared on the left. All right, it's a 0, believe it or not. And on the right, I have an ax squared. I don't have a bx squared. I have a bx and a b times -4. But I do have a c times x squared. So that means that 0 has to equal a plus c, because the amount of x squared on the left has to equal the amount of x squared on the right. Well, I know a is 1/4, so I know c has to be -1/4. And that is my recommended method for finding the a, b, c's, whatever. Is first use up all of your convenient values of x, and then instead of trying to pick other values of x to plug in to find the rest of the stuff, just say, I'm going to equate coefficients. I know how much x squared I have on the left, I know how much x squared I need to have on the right. That's going to allow me to find the remaining thing. So then this is equal to the integral of 1/4 over x minus 4 plus b, which is 2 over x squared plus -1/4 over x. And those are all things that are not too terrible to integrate. Let's see. It's going to be 1/4 natural log of the opposite value of x minus 4. the 2 over x squared doesn't get a natural log, right? That's 2 times x to the minus second. And its integral is 2x to the minus first over minus 1. Or if you prefer, you can write that as negative 2 over x. And then minus 1/4 natural log of the absolute value of x. Let's see. Good times. Let's see how much time we got. Okay. Let me grab one thing here. Yeah, you're okay. So let's look at some other problems. Let's look at another one with an irreducible quadratic factor. I know where it is. Let me just find it. Make sure I didn't put this on here. I see one thing real quick like here. Okay, I did not. Sorry, there we are. Okay, let's try doing this. The integral of 3x cubed minus 4x plus 2. Divided by x to the 4th minus 2x cubed plus x squared. All right, so can we use partial fractions? Probably. It looks like it factors. I mean, it definitely factors. You definitely factor out an x squared from the bottom. So it definitely factors. The thing is, you do want to factor as fully as possible, but it definitely factors. Degree on top is less than the degree on the bottom, so we're good to go. So this bottom factors as, let's see, that's x squared times x squared minus 2x plus 1. And then this factors further as x squared times x minus 1 quantity squared. So I'm going to write my partial fraction decomposition, 3x cubed minus 4x plus 2, divided by x to the 4th minus 2x cubed plus x squared, as, well, first of all, I'm going to rewrite the denominator, x squared times x minus 1 squared. I'm going to write that as a over x plus b over x squared. Right, so you want x squared in all the lower powers, and then you also want x minus 1 squared in all the lower powers. C over x minus 1 plus d over x minus 1 squared. Again, there are no irreducible quadratic factors here. Right, there are no x squared plus 1 or x squared plus 5 or x squared plus 9 or x squared plus 10. Right, things you can't factor with real numbers. I should point out, although I hope it doesn't come up, but if someone gave you a problem like this, 1 over x times x squared minus 2, that's not irreducible either. This totally factors, it just sucks. Something like this would factor as 1 over x times x minus the square root of 2 times x plus the square root of 2. That is a legal factoring, right? That's legitimate real numbers. They're not nice real numbers, they're irrational, but they're still real. So something like this, although you might think it doesn't factor, as far as partial fractions are concerned, this totally factors. And we would do something dumb, like write it as a over x plus b over x minus the square root of 2 plus c over x plus the square root of 2. And then we'd have to find A, B, and C, and they're probably not very nice numbers. But yeah, that totally is a legitimate thing that happens. Probably won't come up, but don't get thrown by it if it does. If you can find the zeros or the solutions of a quadratic, it factors. If they're real, it factors, right? The things that make this 0 are the square root of 2 and the negative square root of 2. Oh, those are real numbers, so it factors. Okay, but back to what we're actually working on. Let's multiply both sides by this denominator. So I'm going to have 3x cubed minus 4x plus 2 equal to, so when I multiply a over x by this, one of the x's cancel. So I get a times x minus 1 squared. When I multiply this by the denominator, the x squared cancel, and you get b times x minus 1 squared. You multiply this by the denominator, one of the x minus 1's cancel. So you get c times x squared times x minus 1. And you multiply this by the denominator, the x minus 1 squared term cancels, and you get d times x squared. And now we're going to start solving for a, b, c, and d by using our convenient values. So our convenient values are 0 and 1. The x equals 0. You get 2 on the left. You get 0 here. You get b times negative 1 squared. You get 0 here. You get 0 here. It looks like b equals 2. Taking x equal to 1, you get 3 minus 4 plus 2, which is 3 negative 1 plus 2 is 1. On the right, you get a 0 here, you get a 0 here, you get a 0 here, and you get a d times 1 here. So d equals 1. But now we've run out of convenient values. We still have to find a and c. Let's start equating coefficients. And the highest power of x looks like it's going to be x cubed. So x cubed, I have 3x cubed on the left. On the right, if you multiply this out, you would have an a times x squared, x cubed. Right, this term here is x squared minus 2x plus 1, and ax times x squared would give you an ax cubed. So I would have an a. Here I wouldn't have a b times x cubed, right? The highest power here is x squared, so I don't get a bx cubed. Here I do have a c times x squared times x, which is cx cubed. I don't have a dx cubed though. So great, 3 equals a plus c, and oh, I don't know either a or c, so I need to do some more work. Let's look at x squared. So how much x squared do I have on the left? None. I'm going to need a little bit more room. So now on the right, we have to be extra careful. If you multiply this term out, we have ax times a negative 2x, which would give you a negative 2ax squared. So the coefficient of x squared there is a negative 2a. If you multiply this out, you'd have x squared minus 2x plus 1 times b, so you'd have a b times x squared. Here you'd have a cx squared times a negative 1, which would give you a minus cx squared. And here you have a dx squared. Now, this might look like too much, but it's actually just enough. We know b and d, so now we'll have two equations with two unknowns, which you can always solve. So we have 0 equal to negative 2a plus 2 minus c plus 1. And I'm going to add this equation to this equation. So if we add those equations, we get 3 plus 0 on the left. A minus 2a is negative a. And then I get a c plus a minus c is no c. And then I get a 2 plus a 1, which is 3. So 3 equals negative a plus 3. So it looks like negative a equals 0. So a is 0. And then since 3 equals a plus c, if a is 0, c has to be 3. So equating coefficients is pretty useful. Again, I think it's best to first use the convenient values, but then after to equate coefficients. All right, let's wrap it up. We still have to do the integral of this thing. So now this is equal to, we don't have any a term, so nothing over x. We have a 2 over x squared. I'm going to write that as 2 times x to the minus 2. We have a c, which is a 3 over x minus 1. And we have a d, which is 1 over x minus 1 squared, which I'm going to write as 1 times x minus 1 to the negative second. Basically, if the overall power of the thing isn't just x to the first in the denominator, I usually like to write it as the negative power to know how to integrate it better. So this is going to equal 2 times x to the minus 1 over minus 1 plus 3 times the natural log of the absolute value of x minus 1 plus x minus 1 to the minus 1 over minus 1 plus c. Notice that we could have done a u sub here and let u equal x minus 1 and then integrate u to the minus 2, but you really don't need to do that. If your u is just x plus or minus something, just treat the x plus or minus something like x and use the anti-power rule, and it totally works. All right, let's look at a
Good question, James.
Go ahead, yeah.
So how do you reduce how do you reduce like everything to just 3 equals negative a plus 3?
So are you okay with how I got this equation?
Yeah.
How about this equation?
Yeah.
Okay. What I did then is I added these two equations together.
Mm-hmm.
So I added the left sides, and 3 plus 0 is 3. And I added the right sides. A plus negative 2a is negative a.
Mm-hmm.
Plus negative c cancels out. And 2 plus 1 is 3.
Oh, okay.
Normally I would show that a little bit more explicitly, but I lack room. So
Yeah.
okay. Once you get down to a place where you have just a and c left and you have two equations, you can either eliminate a variable by adding things together, or you could have also like solved this equation for c and then plugged it in for c there. That would also work.
For sure. Thank you, James.
Oh. So let's look at one of these irreducible quadratic factors. So let's say we want to find the integral of x plus 1 over x cubed plus x. Still meets all the criteria for partial fractions, right? The rational function, degree on top is less, and the bottom does factor. So I'm going to write this as x plus 1 over x times x squared plus 1. And that does not factor anymore. So let's go ahead and make a similar mistake I made before. I'm going to just say, well, let's say we could do this as a over x plus b over x squared plus 1. It's not going to work. Why isn't it going to work? Well, because if I multiply both sides on the common denominator, I'm going to get x plus 1 on the left. And it's going to equal a times x squared plus 1 plus b times x. So it's going to fail for the same reason the other one did. A is going to have to be two different things. A needs to be 0 so that I don't get any x squared over here. But a also has to be 1 so that my constant term ends up being 1. And b would be 1. Doesn't work. A can't be two different things. A is a constant. It's just one thing. And the issue is, what we actually need here, whenever you have an irreducible quadratic factor, meaning a quadratic factor that cannot factor, or doesn't have any real zeros, you need a linear thing on top of it. You need a bx plus c. That's what we need. The reason we need it is because the algebra doesn't work if we don't have it. So then we do the usual thing. We pick convenient values of x. So there's only one convenient value of x here. It's x equal to 0. Right? It's again, the convenient values of x are values of x that make something in the denominator in your original expression 0. So x could be 0. So on the left I get 1. On the right I get a times 1 plus bx plus c times 0. So a equals 1. Great. Now I'm out of convenient values. So we start equating coefficients. My highest power of x is x squared. So I'm going to say, all right, x squared. How much x squared do I have on the left? I have 0. And you can either write 0 or you can write 0x squared. So you can say 0x squared On the right, I would have an ax squared. I would also have a bx squared. Cutting out the x squared, I see that 0 equals a plus b, but a is 1, so b has to be -1. All right, and now I want to figure out what c is. So now I go down to the next power of x. So I go down to x. So on the left, there's 1x. On the right, there isn't any a times x. Right? There's an a times x squared, and there's an a times 1, but there isn't an a times x. There is a b times x squared. I don't need that. There's a c times x. So c is equal to 1. Great. So now I'm going to write my integral as the integral of a over x plus bx plus c over x squared plus 1. And then here's the thing that's almost always true. I don't think it's never not been true. You always want to break this up, right? Whenever you have an irreducible quadratic factor, if you get both of these being not 0 on top of it, you want to break them up into 2 different fractions. I really, really, really want to write this as the integral of 1 over x minus x over x squared plus 1 plus 1 over x squared plus 1. And I'd like to erase some stuff if that's okay. I'm going to erase the stuff down here, but I want to make sure you guys don't have any questions before I erase it.
I have a question, James. So we don't do like one of those like x squared and like zero x squared equals ax squared plus bx squared. We don't do that for the plus 1 because that's just a constant.
I'm sorry, say that again.
Yeah. So you know how for like x squared and just x, we set them up to equal ax squared plus bx squared or cx. We wouldn't do that with our 1 that we have in the beginning. Right?
But so here's actually the thing. You could do that, but that's actually equivalent to setting x equal to 0.
Okay.
Because if you're setting x equal to 0, you're saying, okay, I'm only going to have the constants left, right?
Mm-hmm.
So if I set x equal to 0 here, I'm just left with 1. And if I set x equal to 0 here, well, this is a bx squared, this is a cx, both of those go away. They're not constant terms. This is 0 here, and I get a times 1. So you totally could say the constant term on the left is 1, and on the right is a times 1. And you do use that sometimes if you don't have x being 0 as one of your convenient values. But it is literally the same as x equaling 0 being one of your convenient values.
Okay, yeah, that makes sense.
But yet, what I also say is some people, not me, and it shouldn't be you, but some people prefer to completely just equate coefficients. And so they would not have done this first step here. And in this particular problem, it's essentially the same, but normally it's usually beneficial to do some convenient value stuff before you start equating coefficients. Okay, now, 2 of these are easy, 1 of these is not. This integral here requires a U-sub. The integral of x over x squared plus 1, you're going to let u equal x squared plus 1. Du is going to be 2x dx. 1/2 du is x dx. So this integral becomes the integral of 1/2 du over u, which is 1/2 the natural log of the absolute value of u, which is 1/2 the natural log of the absolute value of x squared plus 1. So that this then you can integrate as the integral of 1 over x is the natural log of the absolute value of x. The integral of x over x squared plus 1 is 1/2 the natural log of the absolute value of x squared plus 1. And the integral of 1 over x squared plus 1 is the inverse tangent of x, or the arctangent of x. You could, but you do not need to use a trig substitution here. If you see 1 over x squared plus 1, You just get to say, I know the antiderivative is the arctangent of x. All right. Let's look at one more problem. I think we got enough time. So we want to do the integral of x squared over x to the fourth minus 1. Okay, still partial fractions. I can factor that denominator. Now the thing is, you want to factor this fully. So you could start by factoring as x squared minus 1 times x squared plus 1. And then x squared minus 1 factors as x minus 1 times x plus 1. So this is x squared over x minus 1 times x plus 1 times the irreducible quadratic factor x squared plus 1. And that's going to equal a over x minus 1 plus b over x plus 1 plus cx plus d over x squared plus 1. And then we're going to multiply both sides by the denominator. So we're going to get x squared on the left. When we multiply by this denominator, when you multiply it by the a over x minus 1, the x minus 1's cancel. So you get a times x plus 1 times x squared plus 1. You get b, so the x plus 1's cancel, you get b times x minus 1 times x squared plus 1. And then here, the x squared plus 1 cancels, and you get cx plus d times x minus 1 times x plus 1. Which it might be easier if we write that as x squared minus 1. It might not be, but I feel like it's going to be. Okay, so now convenient value time. Let's make x equal to 1. So if x is 1, I get 1, I get a times 1 plus 1 times 1 plus 1. I get b times 0, c x plus d times 0. So a is 1/4. Let's make x equal to -1. I bet we're going to get b equal to -1/4. Not 100% positive, but I'm pretty positive. -1 squared is 1. A times, that's 0, that goes away. B times -1 minus 1 is -2. And -1 squared plus 1 is +2. And then -1 squared is 1 minus 1 is 0. So b is indeed -1/4. And now we're out of convenient values. There's nothing else we can pick for x that's real that will make anything 0. So then we start equating coefficients. What's the highest power of x on either side? X cubed. On the left, we have 0x cubed. On the right, if you multiply this out, you have an x times the x squared, which is x cubed, so you have an ax cubed. You definitely have a bx cubed. And you definitely have a cx cubed. But you do not have a dx cubed. A plus b is 0, so c also is 0. Right? A is 1/4, b is -1/4, so that cancels out and you have 0 equal to c. Okay. Let's look at x squared. X squared is going to be a bit trickier. We have 1x squared on the left. If we multiply this out, this multiplies out as x cubed plus x squared plus x plus 1. We multiply this out, this multiplies out as x cubed minus x squared plus x minus 1. So it looks like we have an ax squared. We have a negative bx squared. We don't have a cx squared because we have a cx cubed and we have a minus cx. We don't have a cx squared. We do have a dx squared. A is 1/4. B is -1/4. So 1 minus 1/2 is d. So d is equal to 1/2. So we end up getting the integral of 1/4 over x minus 1 minus 1/4 over x plus 1 plus 0x plus 1/2 over x squared plus 1, which is not terrible to integrate at all. That's going to be 1/4 the natural log of the absolute value of x minus 1 minus 1/4 the natural log of the absolute value of x plus 1 plus 1/2 arc tangent of x plus c. All right, let's call it a day. That's a lot of integrating. Yeah. Hopefully you guys found that illuminating. We will do more on Thursday. I have office hours tomorrow at the usual time, which is 9 o'clock, and also at 2 o'clock. And I will see you guys on Thursday.
James,
Yes.
how come for that last term, our 1/2 divided by x squared plus 1, how come it turned out to be arctangent? Could we have used also an ln, or?
No, we cannot use a natural log here.
Oh, how come?
Well, because, so if you use a natural log, right, if you said your integral is the natural log of x squared plus 1, what's the derivative of the natural log of x squared plus 1?
I don't know. Sorry, James. I don't know that one off the top of my head.
Natural log of x.
Oh, 1 over x.
Right. And the derivative of the natural log of some stuff is 1 over the stuff.
Oh, then times the derivative of that stuff.
We don't have the derivative stuff on top. Right?
Yeah.
Whereas with this previous problem, when we have the x over x squared plus 1, that's why we ended up getting the natural log of x squared plus 1 times 1/2 as our antiderivative, because the derivative of this is 1/2 times 1 over x squared plus 1 times 2x, and 1/2 times 2x gives you an x on top.
Oh, okay.
But in general, when you're integrating, when you have a constant over like x plus or minus a thing, you get the natural log. But when you have a constant over any other power of x other than 1, you're not going to get a natural log.